In 1956, when President Dwight D. Eisenhower signed the Federal Aid Highway Act, people believed they were witnessing the dawn of an unprecedented era of durable infrastructure. More than 66,000 kilometers of interstate highways were planned like steel arteries running across a continent connecting cities, factories, and the industrial imagination itself. But few realized that this moment also quietly triggered a silent race, one in which the opponent was not another nation, not another company, not even another human being, but the bridges themselves. In the years that followed, trucks grew larger, cargo grew heavier, and freight efficiency was pushed into territory that early 20th century steel bridges were never designed to survive. Drivers saw only the road ahead, but beneath them, hundreds of thousands of joints, rivets, and load-bearing members were enduring stresses far beyond what earlier engineers had predicted. And then reality began. To surface, bridges cracked, bridges sagged, bridges failed. A wave of technical reports appeared, many repeating a chilling conclusion. Trucks do not only consume fuel, they consume infrastructure. Every axle, every wheel, every kilogram of payload acts on roads and bridges in magnitudes people of that era never truly imagined. And freight transport, once celebrated as the bloodstream of the economy, suddenly revealed a darker side. It could become a threat to the very infrastructure it depended on. Today, when you see a truck with wheels seemingly floating, an axle lifted mid-journey, that is not a whim. It is the distilled outcome of nearly a century of collisions between economic demand, legal regulation, and the physical limits of steel. To understand why those flying wheels exist, we have to trace the story back through fragile bridges, accidents archived in technical libraries, and the quiet war between heavy loads and the structures forced to carry them. In the early decades of the 20th century, steel and concrete bridges were not the material marvels we know today. They were designed for a world where the heaviest trucks weighed only a few tons, not modern highway beasts, pushing 40 tons and beyond. Bridge design then leaned largely on static loading assumptions, horse-drawn wagons, early automobiles, pedestrians, loads that engineers could describe, predict, and budget for. Industrial trucking shattered that mathematical language. Steel spans carry loads by distributing forces through main girders, cross beams, and X-bracing members. But as freight weight rose exponentially, the forces transmitted at the wheel deck interface did not merely rise in a smooth, linear way. They arrived as concentrated pulses. Early rubber tires, without today's refined suspension systems, generated vertical impacts, dynamic loads that accelerated material fatigue far faster than static weight ever could. The famous Tacoma Narrows Bridge collapse in 1940, though primarily driven by wind-induced resonance, still forced engineers to confront an uncomfortable truth: infrastructure could no longer be built on industrial intuition. If wind could destroy a bridge, then truck loading hundreds of times heavier in direct mechanical effect could not be treated casually. After numerous smaller bridge failures repeated across the United States and Europe, lawmakers faced a blunt conclusion: upgrading every bridge to match the modern trucking era was financially impossible. So the solution had to come from the trucks. This is where the bridge formula was born. It was not merely an equation. It became a rule that reshaped almost every heavy truck design for the century that followed. The formula links axle spacing, axle count, and total weight distribution to ensure that the load applied to bridges stays within design limits. From that point on, every centimeter of frame length, every axle placement, had to obey a strict structural logic. It was no longer build the truck as long as you want. It became build it this way so it doesn't kill the bridge. If physics is the foundation of infrastructure, the bridge formula was the first legal framework that taught trucks how to exist inside a world of fragile spans. As regulators began to realize that each axle produces a different level of stress on the road surface, a new way of thinking emerged: if infrastructure wears out because of the frequency and intensity of loading, Why not tax based on those very factors? Instead of taxing by total weight alone, some systems began taxing by the number of axles on the ground. This was a shift from weight tax to something closer to surface damage tax, an approach more aligned with real-world mechanics. Roads do not fail simply because a vehicle is heavy. They fail because of how weight is distributed per axle and how many cycles of loading repeat over time. A 20-ton truck on 2 axles damages pavement more aggressively than a 20-ton truck spread across 5 axles. In this new logic, axle count stopped being a mechanical detail. It became a financial variable. Freight companies realized that every extra axle did not only add drag and complexity, it could also increase tolls, taxes, and long-term operating costs. And that created a paradox. More axles protect bridges by spreading loads. But more axles also raise operating expenses. What followed was an invisible negotiation between regulators and industry. Governments wanted to preserve infrastructure. Companies wanted to preserve profit. The lift axle became the bridge between those opposing goals, because it can rise when unnecessary and drop when heavy loads demand it. A truck can effectively change its configuration depending on context. When running empty through a toll point, the lift axle is raised, turning the vehicle functionally from a 4-axle setup into a 3-axle one, reducing fees. When hauling heavy freight, the axle drops, satisfying bridge loading rules and spreading pressure. This is where mechanical engineering crosses into political economy. The truck stops being a purely physical machine and becomes an entity operating inside a legal system. Each wheel becomes a tax point. Each lift axle activation becomes a strategic cost optimization. If infrastructure is the playing field, axle taxation is part of the rulebook, and the lift axle is how companies learn to play that rulebook intelligently. As freight competition intensified in the late 20th century, every small factor inside a truck's journey became a variable in the profit equation. Fuel, tires, road wear, delivery time, tolls, each minor cost compounded into the difference between profit and loss. A truck was no longer just a carrier. It became a living mathematical model. In that environment, the lift axle evolved into a mobile economic module. With one action, the truck can redistribute weight, change its wheelbase, reduce rolling losses, and alter its axle-based fee profile. A 3-axle truck can become 4 axles when needed, then return to 3 when it's efficient. This isn't just mechanical transformation, it's strategic flexibility. Large logistics firms began modeling profitability around lift axle usage frequency. One axle does not only protect a bridge, it protects the balance sheet. A well-optimized fleet can save millions annually by reducing rolling resistance on empty runs and lowering axle-based fees at toll stations. Internal industry studies have highlighted another revealing detail. A significant portion of truck travel time is spent running empty. That means for hours at a time. Part of the vehicle's structure is doing work that produces no value, yet still generates cost. Engineering needed to answer one question. How do you stop that extra body from charging you rent? The lift axle became a brilliant solution. As a result, the shape of modern trucks is no longer designed solely for maximum hauling capacity. It is designed around a dynamic balance between infrastructure durability, operating cost, and configuration flexibility. Every axle, every air suspension bag, every stretch of frame reflects thousands of hours of simulation-driven optimization. In this era, the lift axle moved from the workshop into the boardroom. It stopped being an accessory and became one of the key levers shaping profitability across global logistics. The earliest lift axles were simple hydraulic systems, heavy, less reliable, and dependent on manual driver control. But modern sensors and electronic control have transformed them into components that can, in effect, decide based on real-time data. Load sensing systems function like mechanical senses. They measure frame deformation, airbag pressure, suspension sag, and from that infer real payload. Algorithms then determine which axle should touch down, which should lift, and what air pressure distribution yields optimal load sharing. Trucks began adjusting themselves automatically to road conditions, payload changes, and even environmental factors. It resembles biological reflex systems. A cat landing from a jump instinctively adjusts legs and spine to distribute impact forces. A modern truck adjusts axles and air pressure to reduce stress on bridges or minimize rolling losses when empty. Engineering, through embedded electronics, has recreated a form of adaptive behavior. Smart control technology also opens the door to machine learning in logistics. Future trucks could learn from data which routes contain weak bridges, where axle-based toll rules are harsher, which grades amplify rolling resistance. Then they could activate lift axles automatically, optimizing energy and cost without the driver touching a switch. Manufacturers are even testing independent electric axle systems, where a lift axle doesn't only lift, but can provide drive assistance when needed, or recover energy through regenerative braking. At that point, the lift axle stops being merely a cost reduction organ. It becomes part of the vehicle's energy architecture. If 20th century axles were rigid bones, 21st century axles are intelligent robotic limbs, self-adjusting, self-optimizing, and adaptive. This evolution is not meant to challenge physics, but to cooperate with it more intelligently. So when you notice a floating wheel on a highway, it's easy to assume it's just a minor mechanical detail. In reality, it is the symbol of a much larger system, one where physics, law, and economics are forced to intersect to keep infrastructure stable. The lift axle is proof that technology does not evolve in a vacuum. It responds to pressure from its era. When bridges weaken, technology adapts. When tax rules shift, design shifts. When freight demand rises, optimization becomes a survival instinct. Bridges no longer stand alone under the burden. Engineering has compensated with intelligence by creating wheels that know when to disappear. In the hidden war between heavy loads and infrastructure, victory does not belong to the stronger side, but to the side that adapts best.